name is Adam Beardsley. I'm a postdoc in the School of Earth and Space Exploration at Arizona State. I work in the low frequency cosmology lab, doing work on radio telescopes. The Murchison Wide Field Array, it's a telescope in the Australian outback. The Hydrogen Epoch of Reionization Array, or HERA, which is in South Africa, and a long wavelength array, which is in New Mexico. The primary science objective that I have is to study something called the epoch of reionization, which is a time in the universe's history when the first stars and galaxies were forming, and they were emitting radiation out into the space in between, and they would energize and excite the gas that's between all the galaxies and actually ionize them. This was a major, what we call a phase change in the history of the universe. Suddenly, things that were happening in one place of the universe were affecting things very far away, which is the first time that happened. There are many, I should say, there are many kinds of radio telescopes. I'll try to categorize into two. One would be a single dish, and you might have seen Arecibo telescope. It's just a giant bowl in Puerto Rico. You may have seen it in pop culture, like the GoldenEye movie back in the 90s, Contact. It's featured in those movies. But these are just, they're big dishes, generally just a single dish, and they collect radiation, radio waves, and try to map out where it's coming from in the sky based on where it's pointed, and other kind of optics and things that go into it. The other type of radio telescope is an interferometer. Most of the telescopes that I work on are interferometers. They are composed of many antennas, and they're all working together. So it's sort of like taking the reflector of an optical telescope and breaking it up into many pieces. Each of these different antennas or receivers, or however we're going to look at it, are collecting radio waves, and then using computers we combine them together. What we're actually doing is correlating them. We're looking at how similar the signals are, and we get information about where things are in the sky based on how those different antennas are receiving similar or not as similar signals. You can think about it as using a computer to do the focusing of the telescope. We also have, this is me walking inside of HERA, the one in South Africa, which is a bunch of dishes, but that is another example of an interferometer. Radio is a pretty broad term, and it generally goes, it's wavelengths of, you could say, a millimeter out to as large as you want to go. A few hundred gigahertz would be the high end of the frequencies, and then for just going down as low as you can possibly go would be like the lower end of radio frequencies. So lower frequencies have longer wavelengths. So the work that I do is mostly in what we call low frequency radio, and so it's generally below a few hundred megahertz. How does that turn into something you can see? So your eyes obviously can't see radio waves. If they could, you would see you'd be blinded with all kinds of stuff that's happening all around you all the time. FM stations, the way we listen to the radio or watch TV, satellites, they all use radio waves. And so it's actually a really good thing that you can't see them, because otherwise we wouldn't be able to see other things because there's just so much going on. But our electronics can see them. And so as a kind of light wave comes in, you can think about it as kind of oscillating back and forth. It's actually an electric field that's oscillating. In the simplest way, a little wire sitting here, as an electric field comes by and oscillates up and down, that's going to induce the electrons to move in that wire. And we measure that and turn that into a computer or a digital signal, something in the computer that you understand. But you can work out how the relationship between the different antennas can be translated into something that can tell you about how much power, how much radiation is coming from a different direction on the sky. So you could, in principle, point in one direction, see how much signal is coming from that direction, then move a little bit, see how much is coming from there, move a little bit, and build up like pixels of an image, and then turn it into a nice little graph that shows, you know, different, whatever you want to show you, the galaxy or another galaxy. The chart project is something that I started up here at ASU. It's a project that's meant to be led and basically done by undergraduates, and it's supposed to be an education project. So the goal of it is to build a radio telescope that can see the sky for under $100. And the reason is, you know, $100 is pretty arbitrary, but it's meant to be a price point that hobbyists or high school classrooms can actually afford. You know, not all high school classrooms can afford that, but you know, it's hopefully a step in the right direction. And students that want to build one of these can learn a lot about electronics, math, programming, all kinds of different skills that go into building these sorts of things. And in the end, they have something that they created. It's a nice, it's a, you know, telescope, and they can actually see something that's coming from the sky. The title chart is actually the completely hackable amateur radio telescope. We're limited by several factors. There's one that's just like what's in the way. So we are trying to see things that are really far away, like billions of light years. But there's a lot of galaxies and things in between us and that. When you're looking out into the universe, the further away you're looking, because light takes time to travel towards you, you're actually seeing things in the past. So the further out you look, you're actually seeing the universe at a younger stage. And if you look far enough away, you're actually seeing like the very birth of the universe. So there's something called the cosmic microwave background, which we generally observe in microwave, which you could say is kind of radio. And that is a signal that comes from about 300,000, 400,000 years after the Big Bang. So in cosmic times, that's very, very short. And beyond that, light actually just can't propagate because there are free electrons and protons in the universe. They're bouncing around and they interfere with the light, and you simply just can't see past that with light. So that would be like the limitation. And the weird thing is that we have lots of data from the cosmic microwave background. Like we see that, if you look up on Wikipedia or something, you can see the nice map. We've mapped it out. It looks really cool. So that's like at one point really early in the universe, and then we have things like galaxy surveys and things that see distant galaxies that are kind of here, and then there's this gap in between. That's the gap that I'm looking for, the epoch of granization, and even before that, before stars form, we call that the cosmic dark ages, because there are no stars. It's just gas. So that whole period we're trying to map out. Nobody has yet seen it. The historian today can look at records and look at artifacts that have survived the ages. With a telescope, you're not looking at like you're not looking at, say, a supernova remnant and studying, oh, what did that star look like before it exploded? You're actually seeing it as it was, like you're actually looking back in time. It's as if you could like have a live stream of the dinosaurs walking around. Like you're actually seeing it, not just studying what is left today.